Here we go. Markus Ojala from Supercell, balancing player experience without players at Supercell with the case study of Moko.
Thank you. Really happy to be here. So going to talk about that exactly balancing player experience without players. And that's about our new game Moko. This is actually mainly work done by my colleagues, but I'm really happy to present their learnings about the game. So I'm Markus. I work as a data scientist in Supercell. Now just about a year in Supercell, but I've been doing machine learning on large scale in the industry for the last 15 years or so. So in Smartly IO and Unity before Supercell. So I guess most of you know about Supercell, but what is Supercell mission? It's actually to create games that as many people as possible play for years and that are remembered forever. So that's what we are here for doing. And if you look at our games, so we were founded in 2010, so we have now 7 live games. And what are we going to talk today is about our latest game, Moko, that was launched earlier this year. And it was kind of an invite-only launch. It's still kind of like we are experimenting what's the game about. So it's a new game. And if you think about our title, so it's about optimizing, balancing the game without the players. So we have been doing this work actually before the game was launched. Of course, applying those learnings even now. So how can you balance your game when your game is not even on launch? So, of course, for our other games, we have a lot of players, but for Moko, that wasn't the case when we started doing these things. So, what is Moko? It's a multiplayer, like players versus environment type of game. So, you are whacking monsters with your friends, you're collecting loot, you are collecting points, and you have maybe your friends or randos there with whom we are playing. So, I have actually quite a lot of technical stuff also in this presentation. So we are using reinforcement learning for doing this balancing. So what is reinforcement learning? Why do we need this? So our use case is game balancing. So if you think about the balancing, so we have different items, different skills or different things. And like when we are developing the game, our developers would like to know that, hey, is this item working? What is the right way to do? Of course, they can try to play the game themselves, but without actual players, it's really, really hard to start doing that. So, and if you don't have human players, we don't really have a way to learn how they would use all of those like gears that we have in the game. So what is reinforcement learning? So that's the actual technical way to solve this problem when you don't know anything about the game. So the beauty of reinforcement learning is that you don't need to give any rules for the players. So you could think about the dog even, that like you are training a dog. You are giving a reward for the dog if the dog does something good. And this is the same idea when we are training bots with reinforcement learning. Bots are basically randomly just doing something, and if they do the right thing, for example, kill a boss or something, we give a reward and say that do more of this. By utilizing reinforcement learning, we can train these type of bots, and this actually enables us to do that massive scale testing. So we can train thousands of AI bots and put those bots to play our new game, and then just observe how are they playing. What happens with all of those items that we have been doing? We can possibly, if we are introducing a new item, see that, hey, all of the bots suddenly start to use that item, and it's too good. So maybe we need to come back to the game design and start balancing the game with these insights that we get from the bots. And the beauty is in that we don't need any data. So of course, let's say that if we would have human player data about the game, we could also utilize other approaches. There's this imitation learning where we can learn how humans are playing. So that's other approach when you actually know how your players are behaving. But of course, if you introduce something new in the game, then you don't have that thing. So you anyway need reinforcement learning type of solutions when you don't have the data about your players. So our main use case is actually about that balancing. So as said, we don't use the bots in Moko for actually opponents. We use them just when we are developing the game and introducing new items in the game. So how it actually worked during the Moco development cycle was that developers were introducing new ideas maybe every 1 or 2 weeks, and then our bot developers basically trained a new model with these bots, and then saw how did these bots start utilizing all of those new skills. Then giving back the results to the developers, so it could be, for example, what was the play time, how fast they succeeded the level, did they use these items that were planned, also visual kind of just play outs of the game, and sharing those back to the developers. And then the design team actually adjusted possibly the gears, and then iteration continued on. So here we can see one example. So this is one fight. So we have basically 4 bots now trained that are actually pretty nicely playing in the game, and we can see what they are doing. So they are going to whack the monster and collect points. So they are actually behaving pretty nicely. Maybe this is something that was intended to happen in this game. This is pretty long video, so we don't need to wait for that. But then the other one, so the next one is going to be pretty short. So it's an exploitation use case. What means that we have a single bot there who had actually very good selection of gears, and it took was it 1 second to kill the boss basically, and that was not intended. So the bot was able to find a combination of gears in which just 1 second he can kill the monster and complete the level. So of course feedback about this bot is that, hey, there is something off with our gears, that please redesign what happened. So we didn't want that you can complete the level in 1 second. So technically, how are we doing this? So we are building an AI simulator. So what is an AI simulator? So of course we have our game. So game consists of the front end or the client-facing stuff, and then we have a server backend stuff. But we are doing a separate build for this AI simulator use case. So it's basically the headless game client, so we are not rendering the UI, what there is happening, but we are still kind of simulating all of the actions that the player could do in the UI. So it's kind of basically moving and hitting a button. And then we know exactly the state where the player is, and then we can simulate what happens. So if we move right, we know what would be our new state. And this is kind of the simulator that we have. And with this simulator available, we can actually run about 1,000 parallel simulators in a single GPU machine. So we can parallelize training these and also simulating different bots, what they are doing. And the parallelism is actually very essential when you are doing the reinforcement learning. So you need to be able to run thousands of these bots simultaneously and then start training. And okay, the maybe challenge part of this is that it's pretty tight integration with the game. So we go actually to C++ code to put our observations from the game, and it's a very tight integration like that. So the downside is that if some developer actually changes the code, our simulator might broke as well. And there are of course other ways that people might just take the visual thing, but that's then the usually much slower approach. So now we are doing tighter integration with the game, but the downside is that it is the break, because the AI simulator is not something yet that our developers needs to take care of. And technically we are doing some Python binding from the C++ so that we can do the simulation in Python. And then how do we train? So it's, as said, so we have that AI simulator that we can call in Python. So in theory, it's pretty simple. So we have compiled our AI simulator, which is that headless client in the Python wheel. We can just import that. And what does the AI simulator take in? It's just an action. So action is something that move right, move up, hit the monster. Those are the actions, possible actions. And then the simulator basically just takes this action and returns the next observation. So observation is basically everything about we know your state, that what is your location, what are your item balances, the status, where are you. And the reward is that we can give you some reward. So if you completed the round, you get a lot of reward. If you maybe hit the monster, you get some more reward. And then we have that agent is the bot basically optimizes what should be the next action. Based on your current state, agent returns that, hey, what should the bot be doing next? And then how have we built this reinforcement learning? So of course, reinforcement learning is nowadays pretty standard solution, but it's still complicated. So we have an in-house solution built on PyTorch and that we are using. There are, of course, other available solutions that you can use, gym environments, for example. We are also looking now at the RL-lib library that provides reinforcement learning solutions out of the box. So on the top right corner, you see like that's a map. That yellow is an area where you can move, and pink is kind of borders where you cannot. Then we have some features about the players. So more technical details, how you start doing reinforcement learning. Of course, you can take some of those libraries, but all of the libraries, what they usually nowadays implement is some form of proximal policy optimization, PPO. PPO is kind of a simple idea, but then a lot of technical details to make it actually working. So there is kind of this deep learning model written in Python. So you have your observation, basically. Observation is that the bottom right corner, so we have features. We know about where the player is. Then we do some kind of encoding about those features. Then we have your time series previous features. And then we are trying to predict your, basically, what is the optimal action and what is the value from this observation. And how the proximal policy optimization learns is that you take some action. If it was a good action, so you got a good reward, we say that, hey, try to do more of this. So it's kind of the idea that it does something randomly. If it was a good thing, we say that do more of this. If it was a bad thing, we say do less. And then the model kind of automatically starts learning. So it starts from scratch doing a lot of random stuff, sometimes doing good things. We say that do more, and the model learns to put those like weights so that it starts to doing more of those good things. This is a bit technical, but then maybe how are we doing then like utilizing this model? So of course, if we are training this all the time from scratch, it's taking a lot of time. So when there is a small iteration, so usually we have some model tuned, like trained on all of the data sets, but then comes a small modifications to the gear. So we can just like retrain the model using like some small modifications, and this saves us a lot of time. And then when we have this model, we have, for example, those gears. So then we are separately optimizing what gears this bot is now utilizing. That can be done by simple genetic algorithms that basically just choose what items or gears I'm now putting for these bots. And then we can start to see, for example, if suddenly all of the bots would like to use certain gear, maybe it's too good. So this is kind of one outcome that we can share to the developers, that what is the gear like allocation that we are now getting out of these bots. Then if you think about the reinforcement learning, so I mentioned about these rewards. What are the rewards? So this is maybe the most challenging part about reinforcement learning in general, that what is your goal? What are you actually going to, what are we rewarding? Of course you can say that, hey, let's reward only if you successfully complete the dungeon. But that's usually too sparse. So like, what it means that if the bot randomly starts moving there, it's really hard to complete the dungeon if you don't get any feedback while you're doing it. So the simplest way to fix this is that you kind of start giving some small reward for doing something that looks okay. So for example, the simplest idea is that, hey, you stay alive. Like every time, like half a second, if you're alive, we give you a small reward. So basically, to stay alive, you might start hitting some opponents and staying alive. Okay, that's the second. So hitting monsters, you get a bit more reward. Killing monsters, a bit more reward. Hitting a boss, killing a boss, and then finally, biggest reward for completely dungeon. So this is basically a possible way to solve this problem, but it's very tedious, kind of manually tuning all of those rewards and trying to make it work. So one, for example, challenge with this type of reward hacking is that, okay, what we observed, we had this squid balance gear, which basically turns the player invisible if they haven't attacked recently. So of course, if you have trained the bots to like get some reward that you hit even all kind of monsters, they will start to hit. But the optimal human strategy is to put this invisible thing on and then just walk past as many things. And this is kind of for the boss, like bots, if they get this intermediate rewards, it's really hard to learn. So this is like, then if we start moving a bit more complex rewards, so then of course we can add some kind of exploration, maybe give just reward for hitting the final boss, like doing this. This is more kind of that we actually also exploring how to solve this. But now with current things that we have done, so the bots start from something, and now they enable that invisibility, so they are actually able to utilize that invisibility and just walk past the monsters without kind of hitting. So it's something that, like, the better you design the rewards and better methods you utilize for that reward optimization. For example, just saying that, hey, it's important that you start moving. So encouraging bots to move as far as possible, basically, or explore the areas. So giving more rewards on that. So it's not direct reward for kind of hitting, but more reward of kind of going somewhere more interesting areas. So there are a lot of these techniques how you can encourage exploration, for example, adding entropy bonuses or adding pseudo counts, but that's kind of also an active research in the industry how to do these things. So to summarize, so what have we been doing? So we used indeed this reinforcement learning for the Moko game. So Moko is a very new game. We didn't have actual players before we started doing this. Of course, now we have players and we could do something more, but then if you actually tune the gears, it's really hard to do it with real players. So we can really fast iterate on the ideas and do this game balancing. But if you look technically about reinforcement learning, it's still one of those things in the machine learning side that are not really solved. There are libraries, but in practice you need still experts who can actually implement this. And I think it's a very interesting problem as well, so our exploration on this reinforcement learning journey continues. So thank you.
Thank you, Markus. Good stuff. Questions?
Yes.
Anyone?
All right, so thank you for the speech. And I'm interested in hearing that how do you address situations where the bot kind of learns a mechanic that works well, but it's for humans really hard to execute mechanically, for example. So how do you address those issues?
That's a very good question. So one thing is that, okay, mechanically you could think that you need to do something too fast. So one way we limit that is that we basically don't allow bots to do decisions kind of microseconds. So it's more kind of that they can take actions every half a second. So that limits also like that, hey, the combination of actions that the bots can take are something that the humans could take as well. It still doesn't necessarily prevent that there are ways that the bots could learn to do more, so then it might come also that when we kind of train the bot, we look what did they actually learn visually, and then see that, hey, if this is something that the humans would like to do. If it's totally something that we don't want the players to do, we might come back to the game design. But I think the main idea is still limiting the frequency of the actions that the bots can do.
Great. Time for one more question. Anyone?
Thank you for the talk. There was this point that you reward for staying alive. Have you found that it's beneficial to reward staying alive instead of penalizing when you die, for example?
Very good question. So what I mentioned, so initially we started off giving a reward for staying alive. I think it's actually the same as like giving a penalty for dying, because you can think that is the same thing, but at the moment we are not using either of those. So as said, so kind of we want to move towards the idea that we kind of give a reward only for completing goal, and then we give reward from some of those exploration stuff. So getting away of this very short-term goals that, like for example, didn't work with this invisibility gear.
Great. Thank you, Markus.
Okay, thank you.